Now let me introduce you B trees. So B tree is one of the indexing technique, I can say, otherwise one of the data structure which is used in indexing. So far we have seen some tree data structure. What is that? ISAM, right? In ISAM, what is the problem is that is static indexing data structure. That means if that tree cannot grow dynamically. That means whenever we insert the nodes, after some time, then they all will go to overflow pages. When they go to overflow pages, then the length of the overflow page, it will form a linked list. And so whenever you are searching for the data after some insertions, then in the worst case what happens is you might fall, I mean your search might fall under that overflow pages, and we have to search all that overflow pages. It might take a lot of time and we have to avoid that. So that's why we go for dynamic indexing techniques. B tree is one of the dynamic indexing technique, otherwise self-adjusting tree, I can say. That means based on your data and based on your insertions and deletions in your data, your tree automatically will get adjusted such a way it has conditions. That's why first of all we have to learn theoretical B tree. That means what is B tree, how it is defined. So why it is, I mean how can we say that it is self-balanced data structure? For that, what are the things we have to do? We will see one by one. So this is a mathematical B tree, otherwise it's a formal B tree. Let's define an order B tree. We usually give an order to B tree. So what does it mean? It is a search tree. First of all, I explain this concept. What is search tree? So you have seen binary search tree, right? In binary search tree you have only one key, but usually in general typical search trees you can have multiple keys. So in a search tree you will have nodes with the keys comma pointers. That's it. So here also in B tree you will have keys comma pointers. Let's take one small example. Let's say these two are the keys 5 comma 10. Then usually they will be arranged in ascending order. The reason for that is we can apply the binary search among them, right? So that is the advantage. That's why I always try to keep my keys in one node in ascending order. That is one thing. Second one, so whenever I have two keys for trafficking purpose, otherwise for searching purpose, I maintain 3 pointers. All the key values lesser than 5 may fall here, and all the values which are greater than or equal to 5 may fall here, and all the keys which are greater than or equal to 10 will fall here. Such a way I design my tree. We will see that later, but you focus on one particular node of B tree. It's a search tree, that's why you will have some keys and pointers. The relation between keys and pointers is always fixed. If your tree has, otherwise your node has x keys, then the number of pointers will be always x plus 1. Remember it, x keys and x plus 1 pointers. So that is a concept. Now we'll see the second condition. In every node other than root, there are at least p by 2 minus 1 keys. What does it mean? We will see. In a B tree, you have a node. Now you know what is node, right? Already I told you. So in a node, there are at least p by 2 minus 1 keys we have to keep. Then only it is order P B tree. So that restriction gives you the B tree a power of self-adjusting. That's fine. So that's why we should keep this condition. I mean we have to maintain this condition. Example, let's say if your tree is order 6 B tree, then in order 6 B tree, so there are, let's read it. In a order 6 B tree, there are at least p by 2 minus 1 keys. 6 by 2, 3, 3 minus 1, 2. So at least 2 keys we have to maintain. That is the condition. Sir, why other than root? Why don't you keep it in root? I will tell you. So root should have such exception, then only we can define it properly. So the reason why we keep only, why we accept, otherwise why we keep an exception to root, I will let you know after some time. So that is better to, so at least this moment you just remember it, because this is not the right time to understand that. Now we will see this one. In every node there are at most p minus 1 keys. So in every node, so let's say this is any node, maybe leaf, maybe non-leaf, maybe root, whatever, it doesn't matter. So we should have p minus 1 keys. So here this floor is not required, of course. This seal is not required, we can say, because it is always integer, right? So p minus 1 keys. So 6 minus 1 keys, 5. So finally in other than root, at least 6 by 2 minus 1, 2 keys. So minimum 2 keys we should keep, maximum 5 keys. That's why the range of keys will be in between 2 to 5 for this tree. That's it. Now one more thing. In leaf, usually, example, let's say this is your B tree leaf. In leaf you will have keys. Correct example, there are 3 keys, 6 comma 8 comma 10. Then what about the pointers? They are useless, right? So usually they will be pointed to null. Of course there are 4 pointers according to the definition, but they all will be set to null. How you implement doesn't matter. This is mathematical definition, right? So when you bother about storage, sir, we are wasting the space for null values. When you really bother about it in implementation, you implement in a such a way that so you don't keep null values. That's a separate issue. So don't worry about it. Now we are just formally defining how your B tree should look like, correct? So what are the parameters or what are the things we should have in B tree? So this is about B tree definition, right? And one more point. The fourth point is in B tree, every leaf, it is about leaf. Every leaf should be in same level or last level, I can say. Every leaf should be in same level. So this condition ensures balancedness, and because of balancedness your tree will have log height. That means log, so I will tell you example, there are n keys, then your B tree will have the height of log n. We'll see that mathematics at this moment. Just remember that because of this condition your balancedness will be ensured. Every leaf should be in same level. So we have to ensure throughout your maintenance. That means whenever you are maintaining B tree, every time at any time you should maintain this condition so that your tree will be balanced. That is the idea. Now so far, so this B tree is defined formally or mathematically, but now we'll see the application of B tree. We use this B tree in our DBMS. Whenever you use this B tree in DBMS, then at that time one more parameter comes into the picture, that is record pointer. Actually in every node we keep some record pointers for every key, because I will tell you the reason. So now wherever there is a key, then we along with that we maintain one record pointer for that key. So this is the idea. You understand what is key, right? So now you should understand what is record pointer. Record pointer is like this. You are searching for a key. You get it, let's say you got it here. Whenever you got it, then we should know generally why you search for a key. So in DBMS, so every key is attached with some record, correct? So when you got the key, then this record pointer will help you to go to the right record and to fetch that. That's it. So such a way we give the record pointers. So now everywhere there will be record pointers. Remember one thing, wherever there is a key, there is a record pointer. So what is the difference between record pointer and these tree pointers? So in mathematics here I define tree pointers, right? Example, these are all tree pointers. What is the purpose of these tree pointers? These tree pointers just helps your search process, that's it. And record pointer helps you in identifying the record where it is. Once you get the hit, that means whenever your search hits is successful, then you should end up with your a record pointer of that key, so that we'll go there and we fetch it. That is the difference. Now we'll see how B tree node looks like. Okay, this is the B tree node structure, whatever it is. So you will have some keys, some record pointers and tree pointers. Tree pointers are for further search and record pointers for whenever you get the key to get the record, and keys are for searching process, right? So we try to understand these things with one example. Like usually example, you have a file, then how a DBMS otherwise how a B tree can be created for given file, we'll see. So we try to do this dynamically. That means first of all we assume that we have an empty file, then slowly we add some data and we try to create a B tree for that. Initially this is your file and you have one block. In that block, so block and page are interchangeable. That means either I can use block, otherwise page, and I already told you the differences between page and block. From now onwards I don't use page concept, but if you want to refer page concept you can refer, but at this moment because it messes up the thing, that means it will unnecessarily give lot of confusion if I use pages, blocks, everything. Correct? The page story is now complete, done. I don't want to use that page story, I always use block. So the difference between page and block is, page is our logical imagination. That means usually table is divided into pages. That pages are going to be stored in block. That's why directly we talk about now blocks. However, your data is going to be stored in blocks. Now example, let's say your file 1 comma a simple file is stored in block number 1. Okay. So this already I told you, every record will have some address, right? That is record pointer, and that record pointer is nothing but block number B1, let's say, comma, which record, like is it first record or second record, that is record offset. So these two together will become record pointer. Usually record pointer size will be greater than block pointer. That's quite obvious, right? So now let's say this is record pointer R1. So what I'm going to do is, whenever you add a new node, or sorry, new record into the page or block, then I start creating my B tree. Now this is my first node in B tree. It's a root first. Of course leaf, correct? Now in this root what I do is I write 1, and once left I have a space. So in that once left I write null, to say that nothing is there at left side. Once right, there is nothing. So I have a space for maintaining record pointer also. Such a way I design my block. Okay, so in my block I have a space for writing tree pointers and record pointers. Now this is example. Here you have a space just for imagination. It's up to you, like wherever you want to keep the space you can, but for visualization I'm saying that, see, key, left side some space, right side some space, and here some space. In that space you write R1. Slowly you understand, don't try to understand everything at a time. Okay, one by one. Now you have a record and we created a B tree. Now we'll see whether it works or not. Suddenly you want to search for one, start at root and search this node. So you get this key 1, right? Then immediately, so you will hit it and we stop the process and take the record pointer R1, directly go to R1. Then you get it, you got the data. Example, search for 5, 1, no, then go to right side of that, right? Then you realize that it is null. Sir, I have a confusion. Sometimes your node has some 5 keys like this, 1 2 3 4 5. Sometimes you might have only one key. How your DBMS will, otherwise how do you know that whether it has only one key or 5 keys? Simple. What we do is, usually, so you are going to store all these in block, right? Whatever the data, this is, let's say, some block. In that block, after 1 I will try to search for the next number. If I don't get it, so there will be null. Whenever in the place of key, if there is something null like this, then I say that, oh, this node has only one key. Otherwise some extra symbol, I keep a symbol like this, end, no keys, no extra keys. Then I search like this, 1. After 1, since 5 is not 1, I will still search. Then I reach this dollar symbol. Dollar means no more keys. So now only I have one key, that is 1, but I want to search for 5. Then what to do? Go right side. So take the right side's pointer of 1. So you will reach here and you realize that it is null again. So this pointer says null means what? Now it is unsuccessful, there is no data, and we stop the process. Understand? Now remember it. I assume that, let's say, this block, let's say this is the block which has lot of space for pointers and keys. So there is lot of space which is reserved, but you are not using, because at this moment we have only one key. Now try to add 2 comma b. Slowly you understand. 2 comma b is added. Then what I do is, first of all, I update my index. How I will tell you. First of all, search for the right position. This is, you have lot of space here, right? So only this is valid space. Everywhere there is invalid symbols, correct? Then search like this. This is my 1. Next you will see a pointer like this. What I do is, at this moment I assume that, let's say, your tree is order 3 B tree. If it is order 3 B tree, since we know that maximum number of keys you might keep is 2, correct? So at any time you are not going to store more than 2 keys. Then I reserve my space like this. This is for pointer, this is for key. Let's say round is for key, this is for pointer, this round is for key, just for our visualization. Now this is for pointer, in that way. So there will be a reserved space. Now everything initially will be null, 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 null. When data 1 comma a is inserted, immediately I will write in the first key space 1. Then here I write null, here I write null, but already this is dollar and this is null. In that way I initialize. Now you see, second time, whenever a new key comes, 2 comma b, what I can do is simply search for key 1, but I want more than 1. So search, you reach here, end of the, you reached end of the valid keys. So this dollar symbol should be replaced with 2 and simply say like this, 2. And one more thing I have forgotten, there is a record pointer here, correct? So you have space for record pointer also. Now here already there is R1. Since R2 is, 2 comma b is added, its record pointer is R2. What you do is, just now added 2, then you write R2. That's it. So this is order 3 B tree implementation. Sir, we have a question. What is that? What if new data is added, that is 3 comma A? I am assuming that a block can contain at most 2 records. Then 3 comma A will be added to the new block. Okay, that record address is, let's say, R3. Now my question is, how you add it? Simple. First of all, I search like this. 1 smaller than 3, go right side. 2 smaller than 3. First of all, search in this box for the occurrence of 3. Then if you keep on doing, then you reach, let's say, we write some extra symbol called end of the block. End of the block. If I do that, then always, my search, these are all programming issues. That's why I don't want to discuss usually, but here I would like to tell for, this moment. So search like this, you reach end of the block. So, but we didn't get 3. Why? There is no 3. Then this is the time to insert. But to insert, I don't have space also, because I have space only for 2 keys. Why, sir? It is order 3 B tree. Why don't you implement order 4? Whatever you implement, after some time you will run out of space, right? At that time I'm talking. Okay. So for simplicity, let's say we maintain order 3 B tree. Then some situation occurs. This kind of situation occurs where you don't have space in your B tree node. What to do? So at that time, so we use an algorithm called node splitting algorithm. Okay, we'll see that. So node splitting algorithm, how that works and how it adjusts the tree, we will see later. Sir, I have a question. Why don't you maintain very big order so that we never get this kind of node splitting? We'll see. For that you have to maintain order 1 lakh B tree. When you maintain order 1 lakh B tree, then maximum number of keys you can have is 1 lakh minus 1, right? Then you will have lot of space. If you have lot of space, then you are not following the tree structure. Usually tree should have levels. If you keep everything, if you maintain only one node in your tree, then it forms a linked list. Imagine the situation where your data 1 comma 2 comma 3 comma 4 comma 5 comma 6, everything is stored in only one block. One block. So 1 lakh or whatever. Then forget about blocks or logical imagination. Example, you are searching for 1 lakh. Then you have to search like this. It takes lot of time. This is against tree structure. That's why, so our node size should be limited logically, and however your physical node structure also limited. Remember it. Logically, your node structure should be, that means node size should be limited. Why? If node size is not limited logically, theoretically, then what happens? You will create a infinite node, first node itself. Then you will be seriously searching linearly. Then you don't get tree benefit. So that's why what you do is, rather than theoretically, that's why we have a restriction that order 3, otherwise order 5. We restrict ourselves to only some fixed size. Now come to databases. In databases also, so we have blocks, right? That block also has a fixed size, right? 2 things. So now don't get confused between logical node and physical node. Now, so there are 2 things. So far we are discussing just logical ideas like how we can create a node and everything. Now we'll come to the physical idea. That means your logic, this is your node, let's say B tree node. This B tree node has some data like this 1 comma 2 comma 3 whatever, and where we store it is a question. Whatever that storage we have is just blocks, right, in DBMS, otherwise in our system. So we have to store your data in blocks. Now my question, should I store my B tree node in one block or multiple blocks? Think about it. So I can say one thing, this B tree node is a collection of collection of similar information, correct? So if you understand one thing, when you are searching for a node, we have to search first of all this entire B tree node, right? So I can say that this is a collectively similar and information which is closely connected. When you have a closely connected information, don't distribute in multiple blocks. What happens? Unnecessarily number of block transfers will be increased. That's why what people realized is, remember, this is very important point, that is from now onwards your logical B tree node, whatever you have in your brain, that should be always, we have to keep in physical block. That's why usually every tree node, every B tree node will be kept in one physical block. Such a way we should plan your implementations, that you remember. So now let's say really if that is the case, now see the problem. There are 2 things. Forget about theory, like theoretical order or anything. Now, so my order is something we know what is order. I will come to order again. Example, let's say you have a block. In that block, only you are able to keep two keys. Let's say, let me ask that question. If new key comes, there is no space to accommodate. What to do? So for that we do the node splitting. Both are same. So there is a mapping between theory and implementation. DBMS has restriction on block. Similarly, your B tree has theoretically a restriction on node. What is that? That's why the restriction on node is every node should have at most p minus 1 keys. Now I will tell you why they kept this restriction in theory. Because we are going to implement these B trees for DBMS. In DBMS, block has a limitation. We have a fixed size. Example 512 bytes. Then we have to restrict our B tree nodes also to some extent. That means we should say that your every B tree node should have some fixed keys. Because if you have infinite keys in your B tree node, then that cannot fit in one block. Then you can't get the advantage of this efficiency. Then unnecessarily you will be accessing lot of blocks. That's why that is a close connection between logical B tree and real B tree. That means theoretical B tree and implementation. Now let's summarize. So usually B tree has some conditions in any order B tree. Why we will have at most p minus 1 keys? The reason is, so that is going to be stored in a block. Then that order is going to decide. So we are going to decide the order based on this block, right? So remember that point. Now, so you understand how to create a B tree, right? Let's add one more point. So we know that now there is a problem with 3 comma a. Whenever you create 3 comma a record, we were not able to accommodate in this tree. Then what to do? Node splitting algorithm we will see. This process is called insertion. From now onwards, what I do is I don't show you tree pointers, this kind of rectangle boxes. I don't show record pointers also, because they are obvious. Whenever there is a key, there should be a record pointer. You just remember it. That's enough, right? So if I remove it, ignore it. Then if I show only keys and the pointers, what about tree pointers? So the tree pointers I show like this. If I show like this, then your picture will be so simple and so many things we can understand. From now onwards, let me do that. Okay. Now let's see insertions in B tree. Okay. So you have order 3 B tree. I am implementing order 3 B tree. Then strictly follow that things. Okay. So in order 3 B tree, one important point is minimum number of keys and maximum number of keys. So we know that it is other than root. So why it is other than root also you will be understanding. Okay. So other than root, minimum number of keys and maximum keys. So minimum keys equal to p minus 1, correct? Sorry, p by 2 minus 1, p by 2 minus 1, which is seal. So 3 by 2, 1.5, 1.5 seal is 2, 2 minus 1, 1. So minimum key is 1. So maximum key is 3 minus 1, right? 2 keys. So at most we can have 2 keys. Remember it. Such a way we should plan. Now this is your data, 1 comma a is inserted. I show how this data will be inserted and how your tree will be adjusted. So 1 comma a, just see the process. So already I told you that we take one logical node. First of all, forget about the space. So don't worry about the space consideration, only focus on these theoretical restrictions. Then we will come to space restrictions. So you have, this is now your logical node. You have, let's say 1 comma a. Then we write here 1. And we know that left side there is a space, right? Here we write null. I don't show, that's why. So once left is null, you should understand that null, and in between 1 comma 2 there is a space. We know that it's a pointer, null, and there is now, that's it, one's left and one side. You have lot of space here. Next, one more node is inserted, let's say 2 comma b. Then what I do is, first of all I try to accommodate 2 in the index 1. After 1 I should keep, but there is a space, then I keep it. So 1 comma 2. I always assume that I have a space first of all. Okay. So only I follow these two conditions. Minimum condition and maximum condition should not be, always should be satisfied. So 1 comma 2. Now 3 comes. When 3 comma c data comes, we try to keep that in your logical node. Then when I keep it, I don't have any space, I don't have any problem in theory, because I have infinite space in the world, but the only thing is these order restrictions. So why order restrictions are there, we will see clearly. Don't worry about it at this moment, blindly follow it. So maximum key condition is violated. What is that? Maximum keys should be 2 keys, but we have now 3 keys. Then we have to do something. So that is node splitting. We'll see node splitting algorithm. Before that, at any time, so initially we had only one key, right? Initially empty. Now, other than root, minimum keys in any node is p by 2 minus 1, 1, but we have 0. But since it is root, root has exception, first of all. Second, now whenever I add one node, yeah, so minimum condition is satisfied, but of course it's not compulsory. Root doesn't have any such restriction. Then 1 comma 2. Now from now onwards, when you satisfy the minimum condition, if you add more data, minimum condition will be automatically satisfied. We don't worry about it, and we start worrying about maximum keys. So maximum keys are 2, remember. So far it's good. When you add 3, there is a problem, correct? So when you add 3, we should do something, that is node splitting. I will tell you what is node splitting and how it works. According to node splitting algorithm, what we have to do is, we have to divide your logical node into 2 logical parts again, like this. So just I am telling first theory, then we implement it. So in theory, we divide this logical node into 2 parts. Then here I write 1, here I write 3, and since I have created these 2 nodes, then I have to index them. That means, there should be one pointer, one key that should point this box and this box. For that, I need one more node. So you slowly understand why I am taking this node. If I take this node, 2's left I can point here, 2's right I can point here, so that it will become search tree. See, whenever you want to search for, whenever you want to get for 1, then you can start here and you can come this side. Whenever you want to go for a bigger value, you can go right side, right? Now remember here, one's right is null, left is null, one's right is null, 3's left is null, 3's right is null, 2's left is 1, 2's right is 3 node. So along with, I am not showing record pointers, but 1 has a record pointer, 3 has a record pointer, 2 has a record pointer. And one more thing, there might be some extra space also. So don't worry about that kind of physical restrictions. We will see that later. Now come to one more, 4 comma d. Then how to insert that 4 comma d, I will tell you. In the place of 4 comma d, what is key value? 4. Only we keep keys in the tree. Start, and along with that record pointer, so that we can at any time fetch that. 4, 2, then first of all search in this node. You don't get it, correct? Then you realize that this is the only key we have. Then we have to go for 2's right for further continuing. So we come here, we search entire thing, unsuccessful, don't stop, take the 3's right, then you end up with null. Whenever you end up with null, then you realize that, see, there is no 4 in the index, then you add it. Where to add? Go back just one step back, and in this node we write it 3 comma 4. I assume that we have a space in this block, okay? So don't worry about it, only these logical conditions we should maintain. Now 5 comma e. If 5 comma e is added to the file, then what we have to do is, we have to add 5 into this tree. First of all search for it. 2. Now you understand the process. Search in this box, you don't get it, then take the right pointer because 5 is bigger than 2. Then search in this box, we can apply binary search. Then 3, 4, then you reach end of the block. When you reach end of the block, stop it and take the highest number, which is 4, then go to right side of 4. We know that key things, right? For 5, should I go to 3's left? No. Then we know we should go to 4's right. That kind of things we can get it from the logic, right? So 4's right actually, but we don't create. Sir, why don't you create separate node like this? Because you said there is no space, right? Simple. The last condition B tree is, all the leaves should be in the same level. Here you formed a leaf and you have 2 other leaves. Are they in same level? No, that's why I don't allow it. If I allow it, then you always will do that. Then you get a skewed tree and you don't get balancedness benefits, right? So your tree is not balanced, then your height of the tree will be very much high. Then this height is very important for any tree. Example, in B trees, if your tree has this much height, okay, so what is the problem? I will tell you. So I am going to future now. In the future, you are going to implement this logical tree such a way that every tree node, these are all nodes, okay, so logical nodes, that means this is our imagination. This is the way we are going to do the operations. I am just teaching you mathematics, how to insert, how to delete, but how to implement them, we are not worrying about storage concern. When it comes to storage concern, every your B tree logical node is going to be exactly stored in one physical block. Remember it. I will tell you the reason. Already I told you some partial reason, but again I discuss it. But at this moment, remember that your B tree node is going to be stored in one physical block. If that is the case, if you have lot of this kind of B tree nodes which are skewed, then example your data is here, then to search for it, we have to access this block, this block, this block, this block. Every block access needs block transfer from secondary memory to main memory, right? So it takes some time, milliseconds. That's why I try to have my tree such a way that it is as much balanced as possible, right? So remember that. So 5 definitely cannot be at right side. We try to keep here itself, but there is no space. Sir, if there is no space, how did you keep it first of all? Just logical imagination. So far we have not implemented, correct? So really while implementing, how to implement I will tell you. So at this moment just our imagination actually. So what I do is, so 5 I'm adding here just for imagination, but I'm going to take this middle one and I will send to the next level. That is called splitting procedure. Okay. So if I do that, what happens you will see. What I'm doing is always from now onwards, whenever a node is more than full, go to the middle element or middle key. Since middle key is 4, so take it and pull it up, take it and try to keep that in the next level. That means in the higher level. Yes, there is a space in this higher level, let's say. So we keep it. Don't worry about space. See the order. If I keep here 4, so maximum key condition is not violated. If I violate it, then only it's a problem. Minimum key condition cannot be violated because when you add more keys, minimum key condition will not be violated. So now you will have 3 pointers, right? Already 2 has 2 pointers, left and right. Now because you added 4, then you got extra pointer. Then what to do I will tell you. Don't disturb this one, keep as it is, 1 here. Don't disturb this part, right? So here this is, so we are splitting it into 2 parts, right? Then we write this 3 node here and here we write 5. In that way we update the B tree. Understand? Now we repeat this process. Let's add 6 comma F. Now start. First of all search for 6, 2, 4. So you reach end of the block. This block does not contain 6. Then what is the highest number which is smaller than 6? 4. So always my idea is identify the number, highest number which is smaller than your, to be search number. So this one 4. Then go to, because since 6 is greater than 4, go right side. Then you search this one, you realize that there is no 6. Then again you continue going right side. When you try to go right side at any time, if there is a null pointer, that indicates that there is nothing to go further. That's why you stop the process and you reach up always. See, in this process always you end up at leaf. In that leaf we always keep, so that all the leaves will be in the same level. Otherwise if you create 6 here, all the leaves cannot be in the same level. That's why we keep in this level. Mr. 5, please adjust with 6, you have space and we are not violating minimum and maximum conditions. So 2, 4, 1, 3, 5, 6. So far we have added lot of keys and remember we have record pointers too. So do not worry about it. Example, let's do the search process again. Example, you are searching for 6. How it works I will tell you. Same way, how you inserted, in the same way if you do, you come here and you get it here, right? For that, how many nodes you are checking? This node and this node, correct? And one more thing, sir, once you get to here, what you do? Along with C, we are going to maintain record pointers of 6. So take it, you will go to the data. That's it. So simple. This is called B tree. Let's add more data so that you can understand that splitting algorithm. 7 comma G. When 7 comma G is added, so here you try to add 5, 6, 7, but node is full, more than full. When node is more than full, then what to do? Always take the middle element. Send it to the next level. Pretend that there is a space first of all. Okay. So 2, 4, 6 is this position. for 6, right? Then update the pointers of this one. 2's left as it is, don't disturb it. 2's right is as it is, but since you added 6, then in between 4 comma 6 5 comes. That means this node, because you split this into two parts, right? Node 1, node 2. This node 1 here, this is node 2, that's it. In node 1 we have 5, in node 2 we have 7. Then students immediately will get one doubt. What is that? Sir, here you said every node should have maximum key condition, right? Even root should satisfy this maximum key condition, but maximum key condition says that root should have 2 keys, I mean maximum, but you have 3 keys. What to do? Apply the node splitting algorithm recursively. That is what node splitting algorithm. So in the process, see what in the process I am explaining you node splitting algorithm. You try to catch it. So always same thing, whenever your node is more than full, go to the middle element always. That is called median. See here we have a single median, correct? So whenever there is a single median, take it and try to keep it in the next level. So there is no next level in the tree. Create a next level. Whenever there is no next level, usually we create next level. Keep 4. You will get 2 pointers, correct? Because whenever you have a one valid key, there should be 2 valid pointers. Already I taught you. So create a node here, create a node here. Then by this time you should get the clarity that, so when you split this node, then you get n1, n2, n1 will be here and n2 will be here. Quite obvious. 2 here, 6 here. So they go along with their pointers also. 2's left, 2's right, 6 left, 6 right. So we don't disturb them, right? So 2's left as it is 1, 2's right is what? 3. Correct? I am writing here. So 2's right is 3. 6 left is something, I think 5, 6 right is 7. In that way we can do this procedure any number of times so that your tree will be growing continuously. Now we have one more thing, how to see the deletions, how to delete data from B trees. We do that later. It is a little bit complicated and there are a lot of ways we can delete the data from B trees. We will see that. Before that, so we will see some of the properties of B tree. We try to connect this theoretical B tree to your implementation. In implementation, so what is this order? How order is fixed? One thing. Second thing. So what is the relation between your node? This is a logical node, right? This is your tree. This is logical node. There is a physical block. What is the connectivity? How these two are related? We will see. Okay. Now see this example. Let's say this is B tree of some order. So don't worry about it. So whenever you have this kind of B tree, then what do you do with this B tree? So we are going to use this tree for indexing, right? Then you will be searching for it more often. So whenever you search some data, then how that looks, I mean how the process goes on, we will see. Example, let's say you are searching for 9. Just observe. First of all, we start here and we realize that by seeing the key value 10, if and all if 9 exists, it should be here itself, right? So it is not there in this block, then I will go to left side. Then I start searching here. 5, no. 7, no. Then I reach end of the block. That means what? There is no 9 here, then I should take 7's right pointer. Then I come here and I search. If you see the process, so maybe sometimes, you know, if you see the idea of search, you are engaged in searching for some time in this block, then you are engaged for some time here, and you are engaged for searching here. But your search is not like this. Search something here randomly, then randomly here, randomly here. Correct? If you understand that, then you can easily understand that since this, so I can say that this entire logical node, otherwise your B tree nodes key values all are collective information. But this data is not at all related to this data, right? I mean not closely related, correct? At least I can say that. So all these keys 10, 20, 40 are closely connected, and if we can keep them in same block, you get the benefit of you can get the save in the time. How can you save the time? Since all these key values are in one block, then one block transfer is enough to do search process, correct? So that is the idea. Example, let's say, so a family, Raju, Rani, wife and husband, and let's say something, their kids, Rakesh and Suresh. Now these are all a family. and usually they are going to meet frequently. That means, Raju and Rani are going to meet frequently. Raju, Rakesh, they want to communicate. For that, you tell me, I mean, they want to have breakfast together, they want to have lunch together, everything. So there are two options. I mean, this Raju, Rani, Rakesh, Suresh, all these people can stay together. Second one, they can be distributed over all over country, right? Example, let's say Raju in Bangalore, Rani in Chennai, and Rakesh is in Mumbai, and Suresh in Kolkata. Imagine that situation. If that is the case, so suddenly for one important decision they want to meet, everyone want to meet because they are a family. Try to understand, since they are a family, then there is a high chance that they communicate more often than they communicate with others. If that is the case, if Raju, Rani, Rakesh and Suresh are in different discs, I mean different blocks, so Bangalore is a block and Chennai is a block and Mumbai is a block and Kolkata is a block, then Raju is trying to visit all these people to meet. Then see, so many block transfers, correct? That's why if all these people are together, if they live together in one place, then just for any communication, there is no delay, right? Quickly, at any time they can just start communicating, no delay. But if this data is distributed over multiple blocks, then you need lot of time. That is the very important point to say that my B tree node, now from now onwards, this is your B tree node in your logical imagination, and in reality to store that B tree node we have blocks. Then you, by this time, whoever watching this video seriously can understand that this B tree node should fit in one block, so that this will be the optimal solution, right? So from now onwards, in the exam if they don't mention also, B tree node is going to be stored in one block. Now here they ask some interesting questions, we'll try to solve them. That question number 1 is, they say that, so given order some P B tree, they say like this, order P B tree with some key values and record sizes, everything, some information they give, and the block size will be given. They say that we have a 512 bytes block. Then what is the maximum order B tree we can implement? Sir, maximum order B tree means infinite. No, you can't implement infinite order B tree. Why? If your order is infinite, then maximum number of keys you can have in a B tree, infinite minus 1. That many keys in a block you cannot accommodate. Then I will take multiple blocks, then you lose the purpose. So far in this 10-15 minutes, what I was telling you? I was telling you that all this logical B tree node should be in one block. For that you can't have arbitrary order. Order should be some value, so that whenever order is P, then this entire logical B node should be able to fit in one physical block. For that, what is the maximum size P we can fix? We will see with some numerical example. Okay. Let's solve this interesting problem. Key size is 16 bytes. Let's solve this interesting problem. Key size is 16 bytes and block pointer size is 32 bytes. Record pointer size is given, block size is given. Now the question is, if a B tree of order P is implemented, then what could be the maximum order we can have? That means, what is the maximum order B tree we can implement? The only restriction we have is, example, this is your B tree node. So far this is just logical imagination. And I assume that, let's say my B tree order is P. Really it is order P B tree. So sometimes what happens, so you keep so many keys, correct or not? But we have a restriction. Whatever the B tree it is, maximum we can have at most P minus 1 keys. Can we have more than that? No. So what we do is, so we go for maximum condition. I will give you the analogy why we have to see the maximum condition. Example, let's say someone is purchasing the house, and let's say that people who are purchasing is Raju, Rani. Okay, this is Raju and this is Rani. And now there are various options they have: 1 BHK, 2 BHK, or 3 BHK, or 4 BHK in that way. Now how they decide? You tell me. So at this moment, since they are newly married, they might need only 1 BHK. But after some time, let's say they are buying it for 100 years. That means, their hope is this house should be useful for 100 years. If that is the case, then should not be, I mean, check for the local optimum, correct? So they should imagine how many children they can have, and what about the relatives of, this Raju side and Rani side, everything. So they have to take care of that. So how they are calculating this thing, you see. So Raju Rani discussed, finally they decided that, so maybe my side at most one relative can come at a time, so we need one room for them. And Rani said, even for me also, my side at most one relative will come. If multiple relatives comes, then I will take care. So please dedicate one room for my side relatives. In that way, they decided that one room for Raju's relatives, one room for Rani's relatives, one room for, themselves, and one room for their kids. So they are thinking that, so they are going to have one kid, otherwise two kids, let's say, two rooms. In that way, they decide, and one, room for bathroom, and one room for kitchen, and one for dining. In that way, finally, this is the maximum capacity they want. 1, 2, 3, 4, 5, 6, 7, 8. So in that way they decide. In the same way we are also, but it doesn't mean that they are going to have always, 8 people or 9 people, correct? They will be having, in the worst case what can happen, at least Raju Rani will be there. That's why minimum 2 people they will be. Maximum 9 people. In that way, here also your B3 node can have minimum P by 2 minus, let's recall the rules, P by 2 minus 1 keys, maximum P minus 1 keys. So we should not go with minimum condition, because, so if you go with minimum condition, then what happens, then suddenly if your node contains more than that, you cannot accommodate. That's why in the reality now space has to be fixed, correct? Because we are going to fix this entire node into a physical block. For that, first of all, we'll see how many members we are going to have in the worst case. In the worst case, any B3 node of order P will have at most P minus 1 keys. Let's cover that. So that P minus 1 record pointers. I am assuming that we are going to maintain record pointer for every key. That is assumption. So you remember one thing, we can also keep block pointer. In the problem, if they don't mention record pointer, then probably, so maybe you are, keeping here block pointer. That means that is alternative implementation. There are 2 implementations possible. In every node, you keep key and its record pointer, otherwise it's block pointer. That is also possible. So many times we have seen it, correct? So at this moment, since in the problem clearly, let's say, otherwise you assume that, let's say, we are directly maintaining the record pointer of that key. Along with that, what we maintain? Tree pointers, correct? So remember. So how many tree pointers we maintain? P tree pointer. Sir, what is tree pointer? Tree pointer is a pointer which is going to point to another tree node, correct? But that is your logical imagination. Now come to physical, physical things. So now we are in reality. In reality, you are going to store this B3 node. Already I told you that we have to keep this B3 node in dash physical block. If you keep your B3 node in block, then this tree pointer is going to point to the next B3 node. That node is going to be a block. Then this tree pointer will become block pointer, correct? So finally, we are going to have P block pointers. So why P? Already you know that. For P minus 1 keys, we should have P tree pointers. So all these things we are going to have in our B tree. But generally you will have some extra information also, like whether it is internal node or leaf. So we ignore that things. Some, I can say header information. So they are particular to a specific implementation, but it's a mathematical problem. So in academics, so that kind of information is not given. So don't use it. Don't solve the problem like this. Sir, what I do is I reserve some space because I have to maintain some control information about whether it is leaf or not, whether it is internal node or not, how many members we have, correct? It will be always useful. How many valid keys we have in this node, but don't worry about that things. When you solve mathematical problems, we should ignore about them, and we assume that, let's say, they take very less space. Now, if I use only these things, essential things, then you understand what should be the maximum order we can implement, right? So P minus 1 into, so I'm just calculating, really if you keep all these things in your physical block, then how much space they are going to consume? P minus 1 keys consume
16 bytes, p minus 1 into 16 plus these p minus 1 record pointers are going to consume 48 bytes, right? Plus these p block pointers are going to consume 32 bytes. But this entire space cannot be larger than your original physical block size, correct? Then only all these things will fit into your physical block. That's why it should be less than or equal to 8192. So you have to simplify it. If I simplify it, what you get is 16p minus 16 plus 48p minus 48 plus 32p less than or equal to 8192. Okay, so it will be 48, 54p and 32. 54 plus 32 is 96p. 96p less than or equal to, you get 8192. See here, I can simplify this one. 32p, right? Okay, this is minus 16, this is minus 48. I can say that it will be 48 minus 16. It will be 64 and it goes here, then it will become plus 64.
Now you get 96p less than or equal to 8192 plus 64. If you simplify it, you get 96p less than or equal to 8256. Then p less than or equal to 8256 by 96. Let me divide it by, first of all, 2. You get 248 is a 24128. Next 224 is a, then 2 to the 4, and this one 128. It will be 64. Then 212 is a to 1032. Then 12 table. 12 8 is a 96. 72. 12 6 is 72. Then 86. P less than or equal to 86. That means maximum order possible is 86. That's it. Now we'll see some properties of B trees, like what is the minimum height it can achieve and what is the maximum height. For that, we assume that, let's say there are n number of keys in the tree, and h is the height of the tree and p is the order of the B tree. With these parameters we are going to derive minimum height. Let's denote minimum height with h min. Okay, h means height and h min is nothing but minimum height possible. So let's say answer is h min. We are going to derive that h min. We don't know what is how much it is, but we use a variable h min. Really your tree has h min height, then the number of levels will be, you know one thing, right? Whatever may be the order and whatever may be the number of keys. If you have height, this is, let's say, B tree, level 1, level 2, level 3. So whenever the height is 2, number of levels will be 3. If your height is h min, number of levels will be, let's write h min plus 1. Correct? So h min plus 1. Question number 1. So I want to have minimum height. To have minimum height, we have to try to complete all our keys as soon as possible. That means, so we should not extend our tree. That means whenever you have a choice to keep your keys in your first level, so keep as many as possible, and after that keep here as many as possible. In that way, if you fill as many as possible everywhere, then quickly your keys will be completed. So your tree will be terminated. So it will have fewer number of levels, right? Fewer number of levels, of course height also. For that, we should be greedy about filling the data. In the first level, keep as many as possible. In the next levels, again keep as many as possible, so that your height will be very less. So we plan that. First of all, let me ask, maximum how many, let's say this is root, maximum how many keys you can keep in one node? So since it is order P B tree, in the first level you can have only p minus 1 keys. We can't keep more than that. Then the number of pointers will be, we know the formula for number of pointers. Whenever you can have p minus 1 keys, then the number of tree pointers will be p. Then there will be p nodes in the next level, right? This. So here we have p nodes, remember it. Since each node is going to have some keys, then how many keys it can have? Everywhere we have to keep as many as possible, right? Now let's focus on the second level. In the second level, there are definitely p nodes, and each node has at most p minus 1 keys, like this. Then total number of keys in this level will be p into p minus 1. Sir, what are you doing? I am just computing total number of keys possible in this tree. In which tree? Height min tree. but you don't know what is h min, right? It's a variable. That's why if we really h min is the answer, it will have h min plus 1 levels. Then we are seeing the number of keys which is known for us. So number of keys are nothing but n, right? So I am going to relate n comma h min. Really this tree has next level, then how many keys that level will have, we will see. Simple. Each node, this node is having how many pointers? P pointers. See aptitude. So how many such boxes? Let's imagine like boxes. How many boxes we have in the previous level? See, P nodes, correct? So these are all P nodes. Each node is having P pointers again. Then how many pointers overall they create? P here, P here, P here. In that way there are P nodes, P into P, P square. So finally P square pointers will be provided, or I can say that P square pointers are created by these nodes in the previous level nodes, and each one is going to point to a node. Then in this level we have P square nodes, and each node is having how many keys? In the best case P minus 1, right? Here best case means for our problem maximum number of keys. So P square into P minus 1. First only one node, that's why number of keys here P minus 1. In the next level there are, because of this first node contains P pointers, there are P nodes. Each one is having P minus 1 keys. In the next level you have P square into P minus 1. In that way, how many levels we have? Remember, h min plus 1. Let's write the equation for that. I am computing finally total number of keys in the tree. That is what my goal. Total number of keys in the first level P minus 1 plus total number of keys in the next level, that will be P into P minus 1 plus the next level keys are P square into P minus 1, so on up to dash h min plus 1 level. See, this is level 1, correct? In level number 1 I can say that it is P minus 1 into P power 0. In this level number 2 it is P power 1 into P minus 1. In the level number 3 P square. In the level h min plus 1, this is level number minus 1, see, correct? So you get here P power h min, right? H min. What is the remaining thing? Into P minus 1. If I take P minus 1 common, then you get what? P power 0 plus P power 1 plus P square, so on. See, level 1, level 2. In level number 1 it is 0. In level number 2 it is 1. Level number 3 it is 2. Level number h min plus 1, it is just simply P of P power h min. Now if I simplify it, so it is GP series. We know the formula, remember. The formula is A into R power n minus 1 by A R minus 1. This is a formula for a series called A plus AR square, so on, A R power n minus 1. If there are n terms in the GP series, the formula is like this. Let's simplify it. So here A is nothing but first term P power 0, right? So 1 into, before that here one more thing, we have P minus 1, write it, P minus 1 into this one, remaining thing. A, what is the first term? 1 into, so in this sequence, ratio is P power, what is that? Number of terms in this one is h min plus 1 minus 1 by R minus 1. Here ratio is P minus 1. So P minus 1 gets cancelled. Then you get P power h min plus 1 minus 1, right? So this is nothing but total number of nodes. Let's say assume that total number of nodes is n. Then we have to find out this h min, which is unknown. Let's simplify it. To come to this point, first of all we have to send minus 1 to this side. It's better. So let's write it. P power h min plus 1 is n plus 1. And now we want h min, right? So let's apply logarithm this time. If I apply logarithm with respect to base P, what happens is P power h min plus 1 base P equal to n plus 1. So here it will be h min plus 1 equal to log of, here I have forgotten to apply logarithm, log n plus 1. You get log n plus 1 base P. Now what is h min then? It will be, let's write here, log n plus 1 base P minus 1, which is nothing but, sorry, it is h, right? N, so it is nothing but h min. H min equal to log n plus 1 base minus 1. Now, one interesting question here is, h min is actually integer, right? But here logarithm, if I apply for n plus 1 base p, that means for n plus 1 if you apply logarithm, the resulting answer is not integer, you get fraction. Then left side is integer, right side is fraction, then we have to adjust this fraction. For that we have to take logarithm's value either floor or seal. I observed for some of the values and I realized that it is actually seal of logarithm. So you can also check it out. Log n plus 1 base p minus 1. Take some small examples of B trees and take that n value and just understand it. So this will be the final answer. H min equal to log n plus 1 base p minus 1. If you come to asymptotic notations, it is nothing but your minimum height of the tree is log n plus 1 is nothing but n, right? I can say log n base p. This minus 1 we can ignore. So in simpler words I can say that log n base p. So it is log. So whenever the tree has log n height, then quickly we can index it. Example, so how it is very important for us, I will tell you. Really, if your tree has the best height, let's assume that there are 2 to the power of 50 records, just for time being. It's a very huge file, then only it will have 2 power 50 records, right? So not only it's huge file, it's a very huge file. So in that one, if I apply B tree, so 2 power 50 records contains 2 power 50 keys, correct? Every record will have one key, that is assumption. Then the height of such tree is log n base p, right? Approximately log n base p, log of 2 power 50 base. So what is the base we should take? It's up to you. It's not definitely 2, right? So we take order 10 B tree, otherwise order 50 B tree or something. Even if you take very small order like log 2 power 50 base 2, then it will become 50, right? So if you take base 2, it's a very small tree like a binary tree, then that will have 50 levels. So 50 block transfers. Usually it's a huge number if you if you come to databases. In databases, every disk transfer is very important for me. So for that what I do is I take a order something like 50 B tree, otherwise order 40 B tree. If I take order 50 B tree, then it would become, see, 50. How to simplify it? It will be 2 power 50 can be written as log 2 power 50 base 2 by log 50 base 2. So it would become, this is 50, right? 50 log 2 base 2 by log 50 base 2 is nothing but 50 is nothing but, so for easy calculations, let's take base as order as 64. If I take order as 64, then that would be easy for me. So what I do is I take here, file is 2 power 50 but order 64 I am taking. So calculations will be easy for me. So log 2 power 50 base 64 is nothing but log 2 power 50 base 2 by log 64 base 2, that is a formula. If I apply it, log 2 power 50 base 2 is 50 by log 64 base 2 is 6. It will become 6 7 point, right? 6 8, sorry, 8. Then your tree height will become 8, and so that only at most 8 block transfers are required for search. That is the power of B tree, right? So usually that's why people prefer B trees in indexing, because whenever to index it, a file with 2 power 50 records, after all you need 8 levels if the order is 50. I go for order 100, then it would become further less, right? Like order, if I take order 100, it would be something around 3 or 4. So even 8 is okay, right? Rather than 50. So this is about B tree and minimum height. We have to calculate maximum height also. We will do that. Now we'll see second problem. What is the maximum height B tree we can have? So you have n keys and height of the tree is, we have to find out. Let's denote it by h max. So what is h max value? And order is given. Now what I want to say is, to have maximum height, try to have as less keys as possible everywhere. So in root, try to have as less keys as possible. We know that root doesn't have minimum condition, then any number of keys we can keep. But in other nodes, we should have at least p by 2 minus 1 keys, remember it. So minimum p by 2 minus 1 keys everywhere other than root. Root doesn't have any such condition. So we do that. So only one key I keep, because that is as less as possible. If I keep one key, then you will produce, otherwise this tree will produce at least 2 nodes. So how many keys we can keep here? Minimum p by 2 minus 1. So from now onwards, this expression looks weird, right? So I mean lengthy for me, that's why I use p by 2 as x. So for me problem will be easy. So p by 2 is nothing but x. Now here we have how many keys? X minus 1 keys. Here you have x minus 1 keys. Since you have x minus 1 keys, this node will produce how many pointers? X pointers. Here this node also produces x pointers. Correct? Now what is my question is, how many nodes they will form? Since every pointer is going to produce or point to one node, then the number of nodes which are created here is x here and here x plus x 2x. So I can say that in this level you have 2x nodes, and hence the number of keys will be 2x into, in each node we can have p by 2 minus 1 keys at least. We can't have less than that, so that's why p by 2 minus 1. But p by 2 is for us x, then I can say x minus 1. Here everywhere there are x minus 1, x minus 1, x minus 1 keys. Such nodes we have 2x into x minus 1. Now let's extend it. If you extend it, next time what happens? Every such node again produces minimum pointers. Minimum pointers are x, correct? So x here, x everywhere, x here also x. Then how many such pointers will be produced? Very simple. How many nodes we have? 2x. Each one produces, these 2x nodes will produce x pointers. So satisfy 2x into x pointers. Each pointer will point to dash one node. That node contains how many keys? X minus 1. So in that way we can understand this one. First level only one key. Second level x minus 1 keys, x minus 1 keys. In the next level we have x nodes, 2x nodes, 2x into x minus 1. So each node of 2x produces x pointers, right? So that's why the number of pointers will be 2x into x, and each such pointer is going to point to a box. That box contains x minus 1 keys in the next level. So now I understand the pattern. So there are how many levels? H max plus 1, correct? We'll see that H max plus 1 levels. In the level number 1, I write like this: level 1, level 2, level 3, so on. H max plus 1th level, correct? In the level number 1, how many keys we have? I'm counting now. So 1 key. In the second level, how many keys we have? Just now we counted, that is x minus 1 plus x minus 1, that is 2 into x minus 1. Plus in the third level, how many keys we have? See here, it is 2x into x minus 1. Then what about third level? Level 1, level 2, sorry, level 1, level 2, level 3, level 4. In the level 4 we have 2x into x minus 1. So slowly I am understanding. 2 into x power 0 into x minus 1, x into x minus 1, x square into x minus 1, so on. This 2 common and x minus 1 common. So I can say that 2 into x power. So this x power how much? Here x square. Here x, so here it is x power 0, correct? So here x power 1. Third level x power 1. Fourth level x square. H max plus 1 level is definitely, I can say H max minus 1, right? So it is level number minus 2. See here, number of, I mean x power dash, that power is number of levels minus 2. You can check it out. This is second level, right? That's why 2 minus 2. Third level 3 minus 2. H max plus 1th level in the final will be H max minus 1. I am subtracting minus 2. Let's simplify it. So you get this expression 1 plus, let's take 2 common and x minus 1 common. If I take x minus 1 common, what happens? We will see x power 0 1 plus x power 1 plus x squared plus so on, right? So how many, what is the final one? It is x power h max minus 1, isn't it? So this will be the idea. So if I simplify it, it would become 1 plus 2 into x minus 1 into, see it is GP series. We know the formula. First term 1 into ratio x power number of terms x power 0 to h max minus 1. So it will be x power h max, correct? So number of terms are h max minus 1 by x minus 1. So this will be the formula. X minus 1 gets simplified. You get 1 plus 2 into x power h max minus 1. This is nothing but n, correct? So where total number of keys. So we have to get this h max value. For that, so what to do? Let's simplify it. 1 plus 2 into x into h max minus 2, correct? So 1 plus minus 2 is minus 1. If I simplify it, you get 2 into x power h max minus 1, correct? Which is nothing but n. But I want h max. For that, we have to send that minus 1 to that side, 2 to that side. Let's simplify it. So what happens? N equal to 2 into x power h max, correct, minus 1. So x power h max equal to n plus 1 by 2, right? Then h max is, let's apply logarithm. If I apply logarithm base x, then you get h max here equal to log n plus 1 base 2, sorry, log n plus 1 by 2 base x, correct? So this is the final answer. H max is log n plus 1 by 2 base x. Sir, what is x? Let's simplify. Here it would be h max equal to log n plus 1 base by 2 base x. X, our assumption is p by 2, correct? That is the final answer. So finally, if you see approximate answer, otherwise asymptotic answer, it is log n plus 1 base 2 can be imagined as log n, right? Log n base p by 2. So did you remember the approximate answer for minimum height is log n base p? Here it is log approximately n base p by 2. That is the difference. So minimum height, maximum height, it is log n, right? Approximately, asymptotically it is same. So that is about B tree properties, like what is the minimum height and maximum height. We proved that your B tree will have always log n height. Okay.